Welcome to our second webinar in series for physical acoustics. I have pleasure in introducing Dr. Gil Averbuch of WHOI Oceanographic Institute, who's going to give us a talk on atmospheric variation observed by infrasonic signals. Dr. Averbuch did his undergraduate and master's in Tel Aviv University, and then did his PhD at Technical University in Delft in the Netherlands. He worked for a while in Southern Texas University, doing infrasonics, but currently he's at famous WHOI Oceanographic Institute doing seismoacoustics, which is a subject dear to my heart, close to my heart, although my interest is mostly short range and at audio frequencies rather than low sound. So without ado, I'll hand over the microphone, as it were, to Gil and let him start. Just a reminder that the webinar is recorded and it will be available later. And if you have a question, you can write it in the chat or ask the question later on. I prefer if we answer the questions after the talk is finished. So thank you, Gil. Please go ahead.
All right. Thank you for the introduction. Thank you for inviting me. As you can see, today I'm going to talk about evidence for short temporal atmospheric variations observed by infrasonic signals. And before I start, I just want to thank my colleagues that worked with me on this topic, Miro, Roberto, Jake, and Steven. Now, the plan for today's presentation is as follows. I will start with some background for infrasound propagation and detection in the atmosphere. Then I'll talk about the motivation for the study, the data acquisition. Then I'll shortly describe the methods that we use to analyze the data. And I will show you some of our results and finish with a summary. So, infrasound waves are low frequency sound that propagates in the atmosphere with frequencies between 0.01 to 20 Hertz. Higher frequencies are audible and lower frequencies are considered as acoustic gravity or gravity waves. And as you can see from this figure, there are different natural and anthropogenic sources of infrasound that can be underground, in the water, or in the atmosphere. So we have here earthquakes and volcanic eruptions and meteors, nuclear explosions and storms. And actually, infrasound is one of 4 technologies that are used to monitor nuclear tests around the world by the Comprehensive Test Ban Treaty Organization. And as I said, all these different sources, they generate infrasound that propagates hundreds and thousands of kilometers in the atmosphere. And whether we'll be able to measure them or detect the signals depends on the state of the atmosphere. Specifically, the combination of temperature, which gives us the adiabatic sound speed, and the winds in the direction of propagation, which are also known as the long track winds, they give us the effective sound speed profile. And this profile tells us how sound propagates in the atmosphere. Just as an example, this figure shows a typical winter and summer atmospheric conditions in the northern hemisphere. In all these frames, the vertical axis corresponds to altitude. The solid lines represent the winter conditions and the dashed line, the summer conditions. So on the left, we can see how the temperature varies with altitude. And we can see that in the troposphere, the temperatures are decreasing, and in the stratosphere, the temperatures are increasing. In the mesosphere, the temperature are decreasing again. And then in the thermosphere, we can see a rapid increase of temperature. The frame on the right shows the zonal wind, which is the wind in the west-east direction. And we can see here that in the troposphere, regardless of the season, the winds are generally blow to the east, and they reach a maximum in the tropopause, which marks the location of the tropospheric jet stream. At higher altitudes, depending on the season, the zonal wind will blow either to the east or to the west. The frame on the right shows the meridional wind, which is the wind in the south-north direction. And the rightmost frame shows the effective sound speed profile for eastward propagation. To obtain these profiles, I used the temperature profiles on the left to calculate the adiabatic sound speed profiles, and I added to them the zonal wind component. Now, just by looking at these effective sound speed profiles and without understanding much, we can see that these profiles are very different from each other, which means that depending on the season, the acoustic waves will experience different propagation conditions. And also, as I mentioned, these profiles are for eastward propagation, which means that if we were to calculate them for different propagation directions, they will also be different. That means that depending on the time and the place and the direction of propagation, the acoustic waves will experience different propagation conditions. Generally, when there is a decrease in the sound speed profile, acoustic waves will refract upwards in the atmosphere. And when there is an increase in the speed of sound, the acoustic waves will refract downwards. This figure shows an example of the simulation results of infrasound propagation in the atmosphere. The frame on the left shows the effective sound speed profile, which is actually the same winter profile that I showed just a couple of slides ago. And the frame on the right shows the numerical simulation results. The vertical axis corresponds to altitude, the horizontal axis to range, and the colors correspond to the transmission loss values, which is the decrease of the wave intensity, or you can also think about it as the signal attenuation in dB. For the simulation, I placed a source right above the ground. And we can see here that in the troposphere, due to the decrease of the sound speed, the waves refract upwards. Then in the stratosphere, due to the increase of the speed of sound, some of the waves refract downwards, and this increase of speed of sound forms the stratospheric waveguide. On the frame on the right, you can see that some of the acoustic energy is trapped between the ground and about 40 or 50 kilometers. Waves with steeper propagation angles can propagate all the way up to the thermosphere, where again, the rapid increase of the temperature leads to an increase in speed of sound that refracts some of the acoustic waves downwards, and it forms the thermospheric waveguide. And here, this is just one example that we see here, two waveguides, but there can be other atmospheric waveguides, and it only depends on the state of the atmosphere. And these waveguides are very important because they facilitate long-range acoustic propagation. We usually use arrays of microbarometers to measure or detect infrasound, and the microbarometers measure the pressure fluctuation in the atmosphere, and these arrays are usually deployed on the ground, but although sometimes we use them on towers or balloons. But for this work, I'm going to focus on the planar arrays that are deployed on the ground. And using multiple sensors have several advantages. One of them is that it allows us to increase the signal-to-noise ratio, which means that we can detect signals even with relatively high or higher background noise levels. And the other advantage is that it allows us to calculate some of the waves parameter that we record in the array. Specifically, we can calculate the back azimuth, which points to the direction from which the wave arrived at the array. Just for an example, let's assume that we have an acoustic source to the east of the array, and we'll have a plane wave propagating from east to west that will cross our array sensors at different times. And using array processing or beamforming techniques, which are based on the time delays between the recordings, we can calculate the back azimuth. So here we would expect the array, the back azimuth, to point to the east, which is where the source was. But this is not always the case, because in the presence of crosswinds, which are winds that are perpendicular to the direction of propagation, the back azimuth will deviate from the true azimuth towards the source. So this is something that we need to keep in mind. And actually, if we know the location of the source, we can use these back azimuth deviations to calculate or to estimate the atmospheric wind speeds. So infrasound monitoring is used in the forensic analysis of events. Like I mentioned, we use it to monitor nuclear explosions, but we can also use it to study physical processes of different sources like volcanic eruptions or earthquakes. And we can also use it to probe the atmosphere, which is going to be the focus of today's talk. And I think that now the first question that I need to answer is, why do we even want to use infrasound to study the atmosphere? So this figure shows the different standard atmospheric measurement or sensing technologies and the altitudes that they cover. So in this figure, the vertical axis corresponds to the altitude, and the horizontal axis, you can see the names of the different technologies. And it's pretty clear that there is a very big gap, somewhere between 35 kilometers all the way up to 70 or 80 kilometers, that we don't really know what's going on there. And although it looks like the lower atmosphere is covered, there are actually some more challenges in the lower atmosphere as well, mainly in the form of spatial and temporal resolution. And if you ask yourself, what does it have to do with infrasound? The answer is that infrasonic waves propagate in these different regions and altitudes of the atmosphere. And when a wave propagates through a certain medium, it captures or encapsulates the information of the medium's property. So now the question is, if or how can we make use of the infrasound signals to learn something about the state of the atmosphere? And this is not the first time that scientists address this question. But previous studies had relatively low spatial and temporal resolution. They had time periods ranging from 30 minutes to hours and days, and there was a big trade-off between the time and distance, or the spatial resolution. And we don't have to be experts, atmospheric experts or meteorologists to know that the atmosphere is changing much faster than that. All we need to do is go outside and we can feel the wind or the temperature changing. And so it's clear that we need to measure it much faster than that. So we asked ourselves these following questions, and I will try to answer them today. The first question is, what is the timescale of infrasound decorrelation? Or in other words, how fast infrasound signals change due to atmospheric variability? And answering this question will tell us what is the temporal resolution that we can achieve if we were to use infrasound to study the atmosphere. We also wanted to know how sensitive are different infrasound characteristics to short temporal dynamics. And can the atmospheric specifications that are based on weather prediction models explain our observations? And finally, we want to know if we can link variations of infrasound signal signals to specific atmospheric phenomena? And I can already tell you that the answer is not yet, but we're not that far from it. So we had two studies that address these questions. One that focuses on the troposphere, the other one focused on the stratosphere. So let's start with the tropospheric study. So trying to answer these questions, we decided to make use of a repetitive sound source that will allow us to acoustically sample the atmosphere in relatively high temporal resolution. And our repetitive source is a daily explosion sequence that takes place at the McAllister Army Ammunition Plant in Oklahoma. And one of their jobs is to get rid of all the munition. And apparently, the best way to do it is by blowing it up. So they have two areas with 26 pits each. And you can see the red stars mark the location of these areas. And you can see we have area 1 and area 2. In area 1, the pits are arranged in some kind of a circular oval shape. And area 2, they're placed along a straight line. And every day, they fill up these pits with all the ammunition. And at 11 a.m. local time, they detonate them in 20-second intervals, with about 2 minutes break between the two. So for this study, we deployed two infrasound arrays. The first one that we can see here is the MCA array we deployed near the detonation site. And it is there to capture the source time function of the explosions. This is our reference array. The other array that you can see here is called the EOC array. We deployed it 54 kilometers to the east, which is aimed to detect only tropospheric signals. This figure shows just an example of our recordings at the EOC array. And you can see here 5 channels that correspond to our 5 elements of the array. And you can see that there is about 20 minutes of impulsive signals that correspond to these explosions. And these impulsive signals are have very broad frequency band, and they're actually audible at these distances. I wasn't expecting to hear them there, but you can really hear these explosions 54 kilometers away from the detonation site. So for the processing of the data, we start with beamforming the recordings from each of the arrays. And beamforming gives us the back azimuth variations as a function of time, but it also gives us the best beam, which is the high SNR version of our recordings. Basically, by doing that, we suppress the background noise. Then, using the best beams from both arrays, from the MCA and the EOC arrays, we're going to calculate the empirical Green's functions. And by doing that, we're going to remove any source effects and generate synthetic signals that any variation in them is attributed only to variations of the atmosphere. And I'm going to talk about it a little bit more in the next slide. Next, we're going to cross-correlate all of our synthetic signals. And that's going to give us the correlation coefficient as a function of time, which is a measure of how the waveforms change over time, and also the time delay, which tells us how the propagation time between the source and receiver change over this 20 minutes. And finally, we're going to compare our synthetic signals with numerical simulations. Just as a reminder for the Green's functions, this sketch that you see here basically it represents the setup of our experiment. We have a source that generates infrasonic waves. They propagate in the atmosphere, and we record them at our EOC array, our receivers. The observed signal can be described or expressed by the convolution of the Green's function, the atmospheric medium's Green's function, which is the impulse response, with the source time function. So we have our observation. This is our receivers. We also have the source reference or the source time function. This is our recordings near the detonation site by the MCA array. So now we can compute the empirical Green's functions of the atmosphere. And this is going to give us a set. We're going to do it for each of the detonations, which will give us 52 empirical Green's functions that implicitly describe the atmosphere temporal variability. After obtaining these 52 empirical Green's functions, we're going to convolve them with the same source time function. And that will give us these synthetic signals that any variation in them is attributed only to variation of the atmosphere. And although we call them synthetic signals, they're all based on our observations. So they capture how the atmosphere is changing. So I think we're ready to move on to our results. And this figure shows our results from January 20th, 2021. Here we show the synthetic signals based on the empirical Green's functions. And there is a lot of information here, so I'm going to go over it slowly. In all these frames, the horizontal axis corresponds to the detonation time. So we have 52 signals with about 20-second time difference between each of them. That gives us almost 1,200 seconds or almost 20 minutes. The first row shows the empirical Green's functions on the left from area 1 and on the right from area 2. The second row shows the correlation coefficient as a function of time. And here from each of these sets, we use the first signal as a reference and we cross-correlate all the other signals with the first one. So it tells us how the signals change or the waveforms change over time. The third row shows the corresponding time delay that is based on the highest correlation values. Now, going back to frame A, we can see that we start with two distinct arrivals, one around 140 seconds and the other one around 142 seconds. And what we see here is that over a few minutes, the amplitude of the first signal is decreasing, while the waveforms of the second signals are slowly changing. Then there is a 2-minute break between area 1 and area 2. And the first thing we can notice when we look at the signals from area 2 is that there is a 2-second time difference in the arrival time. Now, these 2 seconds are associated with about 800-meter difference between a distance of 800 meters between area 1 and area 2. But when we look at the waveforms now, we can see that we only see one distinct arrival. So the first arrival that we saw in the previous set completely disappeared, and the waveforms are very different than what we saw also in the previous set. And just as a reminder, there is only a 2-minute difference between the first set and the second one. Looking at the correlation coefficients, we've seen from both areas how the correlation values decrease quite fast. They decrease actually faster from the second one than the first one. But what it tells us is that the waveforms are changing in timescales of tens of seconds or just a few minutes. And when we look at the time delays, in frame E, we can see this oscillatory behavior. And this is associated with the circular or oval shape of area 1. And in frame F, we can see a steady increase of the time delay, which is partly explained by the linear geometry of area 2, but there is more into it, and I'll come back to it later. Now, looking at the simulation results, frame A shows 3 sound speed profiles, or effective sound speed profiles, and we obtained the atmospheric conditions or specifications for the simulations from the NCPA G2S server. So there are 3 effective sound speed profiles at 3 different times. This is 434, 534, and 634 UTC, which correspond to 1034, 1134, and 1234 local times. So it's about 1 hour before the detonations, at the time of the detonations, and 1 hour later. Frame C shows the along track winds. These are the solid lines, and the cross track winds, these are the dashed lines. And we can see that the cross track winds are very weak at these 2 or 3 hours. Frame B shows the narrowband simulation results from the test site all the way to our EOC array, 54 kilometers away. And what we see here is that all of the acoustic energy that arrives at the array is trapped within the first 2 kilometers of the atmosphere. And frame D shows the broadband simulation results based on this, the 3 sound speed profiles that are shown in frame A. So we have the red, green, and blue waveforms that correspond to the 3 different profiles. And what we see here is, first thing is that over time, we see that the signal is arriving earlier, which means that the waves propagate faster over time. The other thing that we see here is that over time, the amplitude of the signal is increasing, which means that the acoustic waveguide between the ground and about 2 kilometers is able to trap more acoustic energy over time. And this is actually something that we see in our observations as well. The purple signal that we see behind the green one is one of our synthetic signals. It's actually this signal right here that has the highest correlation coefficient with this green simulated waveform. And we can see here that the higher amplitude signal is captured pretty well by the atmospheric models, but the preceding waveforms are not captured, basically. So we see that the atmospheric conditions can partly explain our observation. But here I want to remind you that this is only one signal out of 52, which means that there are other 51 signals that are very different than the one I showed you, and they are very different than our predictions based on the atmospheric models. Moving on to another day, this is from February 5th, 2021. Again, we start here with 2 distinct signals, but now what we see is that the amplitude of the first signal is slowly increasing over time. And we can see it while we get to the other set of detonation, that the amplitude of the first signal is increasing, while the waveforms of the second signal are slowly changing over time. Also here, we see this 2-minute time difference between the arrival time. But now it's the other way around, because on this day, they started with detonations in area 2, and then they continued to area 1. Also here, in both sets, we see a pretty fast decrease of the correlation values, which means that the waveforms are changing within tens of seconds or minutes. And when we look at the time delays on the left, we see this steady increase. It's like before, partly explained by the linear geometry of area 2. And we see this oscillatory behavior that is associated with the circular shape of area 1. Now looking at the simulation results, we start by looking at the broadband simulations in frame D. We see in the red waveforms, there are two distinct arrivals, where the first arrival is associated with this faint branch of energy that we see in frame B that is almost parallel to the ground. So this signal propagated along the Earth surface towards our receiver array, and the second signal corresponds to the propagation path for the higher altitudes. And when we look on the following predictions, which are the green and the blue waveforms, you can see that we slowly see that the amplitude of the first signal is decreasing until it disappears, and you can see that we cannot see it at all in the blue waveforms, while we keep the amplitude or the second signal. And this is actually pretty interesting, because when we look at the data, we saw that the amplitude of the first signal is increasing over time. So there is some disagreement here between our observations and the models. And again, when we compare our observations, this is the purple signal with the green one, which is our predictions. And we see that the second signal is predicted pretty well by the weather prediction models, but not the first signal. All right. In this figure, we plot all the time delays from area 2, which is the linear area. The black dotted and dashed lines correspond to the expected time delays based on the geometry of area 2. And what we see here, the color dots correspond to the time delays from 3 different days. I showed you the results from 2, but we had another day that we studied. What we see here is that the geometry of the area can only partly explain the observed time delay, which means that the excess time delay is associated with the variation of the atmospheric conditions. Specifically, it tells us that the signals arrive earlier, which means that they propagate faster. And this is in line with the trends that we see based on the numerical weather predictions. Moving on to the stratospheric study, here we use the same source. This is at McAllister. Now we have a reference array called the MCB array. But for the stratospheric study, we deployed an infrasound array 250 kilometers to the west of McAllister. We deployed it at the Wichita Mountains Wildlife Refuge. And you can see it here, this is the WCT array. And the campaign took place during the summer, when the stratosphere facilitate westward stratospheric propagation, but not tropospheric propagation, which means that we know that any signal that we'll record in this array propagated only through the stratospheric waveguide. Now, here we use the same methodologies for our data analysis. And frame A shows, again here, the synthetic signals based on the empirical Green's functions. Here we plot all the signals in one frame. And when we look at the waveforms, we can see that we start with the waveforms are relatively similar to each other. And we see again this oscillatory behavior, which like before is associated with the oval or circular shape of area 1. And this is quite surprising that we see this effect also 250 kilometers away from the source, where the distance between these different pits is about, it's in tens of meters. Then after 400 seconds, we see this very rapid disturbance of the waveforms. Then there is, again, we see relatively similar waveforms that arrive slowly faster over time, which is similar to what we saw before. This is probably due to the warming of the atmosphere. But again, after at about 1,000 seconds, there is again this rapid disturbance of the waveforms. Just to highlight these differences, you can see I plotted the purple, green, and yellow waveforms are plotted in frame B. And you can see how the purple and yellow waveforms are very similar to each other, while the green one is completely different. Frame C shows the correlation coefficients. These are the black dots, and you can see how they vary over time. And the purple dot, or the maroon dots, correspond to the transmission loss values, which is a measure of the signal's energy. And we see here something very interesting, that the signal energy follows the trend of the correlation coefficients. And we don't really know how to explain it, but we see it also on other days. So this can be a very interesting research topic if anyone is interested. Frame D on the right shows the spectral content of the black curve that we see on the left. So we did a spectral analysis to how the correlation coefficients change over time. And what we see here is that the three dominant frequencies that represent these variations, they have their periods correspond to 172, 317, and 740 seconds. And using these frequencies, we constructed this gray curve here that follows the variation of the correlation coefficients. And 317 seconds is actually, it's the atmospheric buoyancy frequency. So our hypothesis, seeing these frequencies and looking at the waveforms, our hypothesis is that the disturbances that we see in the waveforms at about 400 seconds and 1,000 seconds are associated with propagation and breaking of internal gravity waves in the stratosphere. But as I said, it's just a hypothesis and we didn't test it yet. Now, looking at the numerical simulation results, here we use the ECMWF ERA 5 reanalysis for the atmospheric specifications. Again, frame A shows 3 effective sound speed profiles at 3 different times, 1 hour before the detonation sequence, at the time of the detonation, and 1 hour after that. Frame B shows our narrowband simulation results, where we can see how the waves first refract upwards in the atmosphere due to the decrease in speed of sound, and then when they reach to the stratosphere, at about 40 to 50 kilometers, they refract downwards when they propagate towards our WCT array. Looking at the broadband simulation results, again, these are the red, green, and blue waveforms, we see 2 distinct arrivals, and these are known as the stratospheric pairs. What we see here is that over time, The first signal is predicted to arrive later over time, and the second one is arriving earlier over time. And these variations in the relative time of between the first and second arrival is associated with the gradient of the sound speed profile at the altitudes of the refraction, so in altitudes of about 40 and 50 kilometers. The black waveform that is behind the green one is, again, is one of the our observations with the highest correlation coefficient with the green, with our predictions at the time of the detonation. And what we see is that based on the atmospheric predictions, specifications predict the second waveform very well. They also predict the first signal, although it's a bit shifted in time, but the shape of the waveform is well predicted at all times. Now, moving on to our results from August 30th, again, we see here it's different day, same story. We start with waveforms that are very similar to each other. Now, about 300 seconds later, there is this rapid disturbance of the waveforms. After that, again, the waveforms are relatively similar to each other. And again, we see a rapid disturbance of the waveforms. If we look at the purple and green and yellow waveforms on the right, also here we see how the purple and yellow waveforms are very similar to each other, while the green waveforms is completely different. And also here we see how the signal energy, which is the transmission loss, follows the correlation coefficient over time. Here you can see again our numerical simulation results. And what I want to highlight here is that 1 hour before the detonations and 1 hour after the detonations, based on the atmospheric specifications, we basically predict that no signal will arrive at the array. The dashed waveforms that you see in the red and blue lines are scaled by about 500. But when we look at the green signal, these are our predictions at the time of the detonations, you can see that this second arrival is predicted very well by the atmospheric models, but they don't predict the first signal that we see in our data. Right. So before I finish, I want to just remind you that you can find everything I presented today in these 2 papers. And also all the data that we use for these studies is openly available via IRIS. The information on how to get the data is in the papers. And if anyone is interested and having some hard time getting it, just send me an email. And to conclude, I want to circle back to the questions I presented at the beginning of the presentation. And so we asked ourselves, what is the timescale of infrasound decorrelation and how sensitive are different infrasound characteristics to short-term polar dynamics? And we saw that the waveforms and amplitudes and propagation times of infrasound signals change in timescales of tens of seconds to minutes. And these changes are associated with short temporal variations of the atmospheric state. We also wanted to know if the atmospheric specifications can accurately explain our observations. So the answer is no, because the available output of atmospheric models is at best every hour. And we saw that our signals change much faster than that. But still, we saw that based on the atmospheric models, we can capture the general trends of our observations pretty well. We also wanted to know if we can link variations of infrasound signals to specific atmospheric phenomena. And like I said before, the answer is not yet, but we saw that variations of the signal's waveforms and propagation time and energy are all related to fluctuations in temperature and wind. And future work should definitely focus on relating them to different dynamic processes like radiations and the propagation of gravity waves or the breaking of gravity waves and turbulence and any other atmospheric phenomena. And finally, these results motivate using infrasound waveform information for atmospheric tomography, especially in atmospheric regions with poor in situ or remote sensing measurements. Thank you for joining and thank you for listening. I'll be happy to answer any questions.
Well, thank you very much, Gil. That was an interesting talk, and you can see, you know, we normally talk about frequencies, orders of hundreds of hertz. Here to talk about frequencies, orders of fraction, 0.3, 0.01 and less. I was going to ask if there is any question. I can see Keith Attenborough already raised his hand, so I let him speak first before I ask my questions.
Sure.
Can I? Yeah.
I've already let Keith to.
Thank you. Please go ahead, Keith.
Yes, hi. Thank you very much. Very fascinating talk. So I want to ask, to what extent, certainly with the lower height propagation, you've taken into acoustic to seismic coupling into account. I mean, do you have any simultaneous geophone recordings? One reason I'm asking is that about around 2005, we did some work with Christian Madses on some of his explosion propagation data in Norway, albeit at rather shorter range than you're considering, 17 kilometers at that time. But we found quite a big reduction in the airborne traveling signal when around about 2.5 hertz, which turned out to be the Rayleigh wave frequency for that particular terrain.
Yeah, so we also had a seismometer collocated with our reference array, and we measured very low amplitude seismic waves over there. So we assume that most of the energy is coupled to the atmosphere. And there is another work by, I forgot the name, and there is another work that used a similar data set or the similar recordings from the McAllister Army ammunition plant. They used seismometers, I think a few hundred kilometers to the north, and they measured there only the coupling of the infrasound locally to the seismometers. So I think most of the energy is emitted to the atmosphere, and very small fraction of it is going to the subsurface.
Sorry, just a quick follow-up. But there is also the chance. I mean, if you can create a Rayleigh wave, however weak, then there's a possibility of an air-coupled wave associated with it. Yeah, going back to you in Detskin Press 1957.
Yeah, of course, some of the energy is coupled to the subsurface, but yeah, I don't see how it affects any of our the results that I presented here.
It's probably to do with frequency, as Keith says. The Rayleigh wave is order of 1 or 2, 3 hertz, but what you reported, if I'm not mistaken, is a lot lower than that.
Oh no! So the frequencies that we use here are between 1 to 10 hertz.
Right.
1 to 10 hertz for the tropospheric propagation, and I think up to 1 to 5 hertz for the stratospheric propagation.
Okay, so in that case, if there is no question, I have one, if possible.
Sure.
The atmospheric conditions change not only temporarily, but also spatially. You're
Right.
talking about propagation over hundreds of kilometers or tens of kilometers. So do you account for that in your modeling? Or do you have a means of measuring, data? Do you have data for that variation along that? Or do you take in a means, some sort of mean average?
Yeah, so definitely the atmosphere is changing spatially, but in both cases we used a 1D atmospheric profile for the numerical simulations, but we did it after careful consideration of how the atmosphere varies in range. So in the case of the tropospheric studies, I think we had only 1 or 2 points of data from the atmospheric specifications, how it changed along the way, and we saw that there is a very small change in this about 50-kilometer distance. And we did the same thing for the stratospheric study. We obtained the atmospheric conditions at different points along the propagation path between their source and our receiver, and we first estimated how it varies in range, and there was a very small variation in this case. So we knew that we can use 1D profiles for these simulations, but definitely sometimes the atmosphere is changing very fast in range, and then you have to take it into account.
Thank you. Is there any questions? I can't see anything in the chat. And if there is no question, I have another one I would like to ask if possible. And that is to do with you know, in your first slide showed many sources of infrasonic sound, both natural and man-made. So the background noise must be pretty high because there are so many. I recall a colleague long time ago contacted us and talked to me about whether they could use infrasound for triangulating meteor drop on Earth, you know, to almost real-time location, locating a meteor, which is possible, but again, the background noise and extracting what you need to know from that is quite difficult. So was the background noise issue for you, or
not so much. So we can think of the background noise in two ways, or there are 2 sources of background noise when we're interested in these specific signals. First is the local wind noise. This is the wind blowing over the instruments that it generates some noise. It's higher frequencies, but this is the advantage of using multiple sensors. If we assume that the noise is uncorrelated between the different locations, by using array processing, we can suppress this background noise and suppress its effect on the signals that we see. The other background noise that we consider when we work with infrasonic signals is, I would say, call it more of the background ambient sound in the atmosphere, and this is generated by some nonlinear interaction of ocean waves that emit a low frequency sound to the atmosphere. These are called microbarometers, and they have typical frequency of 0.2 hertz. and it's very distinct in all of our recordings. So this is something that you need to, we are aware of it, and if the frequency bands don't overlap, then it doesn't really matter. If the frequency bands of interest overlap this 0.2 hertz, then we need to make sure where the sound is coming from. If the directions are different, then it has less of an effect. But essentially, if you have these microbarometer signals coming from the same direction that your the source is, and it also has the same frequency spectrum, then you wouldn't be able, it will be very hard to distinguish between the two.
Right. Thank you. Are there any questions? I can't see any.
No, there are no. The Q&A list is empty. So no one.
Okay, so in that case, I thank you very much, Dr. Gil Averbuch, for your interesting talk, and all the best in your future research in seismacoustics.
Thank you very much. Thank you for inviting me.
Thank you, and I hope we'll soon be able to announce another webinar in a similar physical acoustics subject.
Yes. So
Thank
we
you
need
very
to-
much,
Mhm.
audience, and see you all soon.